What do neurodegenerative diseases, gerrymandering, and ecological inference all have in common? Well, they can all be studied with Bayesian methods, and that's exactly what Karin Knudson is doing. In this episode, Karin will share with us the vital and essential work she does to understand aspects of neurodegenerative diseases. She'll also tell us more about computational neuroscience and Dirichlet processes, what they are, what they do, and when you should use them. Karin did her doctorate in mathematics with a focus on compressive sensing and computational neuroscience at the University of Texas at Austin. Her doctoral work included applying hierarchical Dirichlet processes in the setting of neural data and focused on one-bit compressive sensing and spike sorting. Formerly the chair of the Math and Computer Science Department of Phillips Academy Andover, she started a postdoc at Mass General Hospital and Harvard Medical in fall 2019. Most importantly, rock climbing and hiking have no secrets for her. This is Learning Bayesian Statistics, Episode 4, recorded October 18, 2019. Welcome to Learning Bayesian Statistics, a fortnightly podcast on Bayesian inference, the methods, the project, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country, and reach a true Bayesian state of mind by visiting learnbayesstats.anvil.app. That's learnbayesstats.anvil.app.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. What's a Bayesian? It's someone who cares about evidence and doesn't jump to assumptions based on intuitions and prejudice. A Bayesian makes predictions on the best available info and adjusts the probability, cause every belief is provisional. And when I kick a flow, mostly I'm watching eyes.
Karin Knudson, welcome to Learning Bayesian Statistics.
Thank you. It's great to be here.
Yeah, you bet. Thank you for taking the time. I'm actually really glad to do this interview in person. Well, first, it's always nicer than an internet chat. And second, it's by far the episode where I know least about the topics we'll talk about. So it's a good thing that you're in front of me because you'll be able to wave at me when I'm beginning to speak nonsense. You know, it's great. I'm counting on you. Before that, I think it would be interesting to have a word on your background. I wanted to know what compelled you to become a researcher in computational neuroscience, but you did your PhD in mathematics, as I said in the intro. So what compelled you to do that?
Sure. So when I started my grad program, I was planning to go into pure mathematics, but I guess I just got sort of tempted away by the appeal of being able to connect my work to science and tangible things around me in a more concrete way. I ended up taking a computational neuroscience class with the professor who became my advisor, and I was just totally hooked. The brain is so complex and so core to who we are as humans, and the project to understand it is just so massive. I couldn't think of anything more interesting to study.
Yeah, I bet that's really fascinating as a topic. And even I, who doesn't understand really well these topics, it's always great to see some talks about that or read books about the brain. You're always amazed about that. But actually, how did you then get into the Bayesian side of the things? I mean, how did you come to Bayesian methods?
Sure. I felt lucky because it was sort of an essential part of the toolkit that the lab that I joined was using. So I guess I learned on the job, so to speak, before taking formal coursework in the area.
Okay.
I use Bayesian techniques now because they're interpretable and effective, and that's what I need.
Yeah. And did you get this training like when you were in your PhD curriculum?
Yes. So my first project when I joined my lab involved using Bayesian techniques.
Okay.
And I think because I was the only pure math person joining the lab at the time, especially, there was some emphasis on, that I could explore those mathematical approaches deeply. And I loved doing that. So that's how I got into it.
But you didn't really get into it like in undergrad or in grad?
No. When I was in undergrad, I still thought I would be a pure mathematician and was exploring the beauties of topology, which was a wonderful topic, but not what I do now.
Yeah, you were like, oh, wow, what's this weird thing, statistics?
Totally.
I mean, is it like chemistry or something like that?
Exactly.
Yeah, that's actually what the guests say on the podcast, is that usually they don't have the a formal training in Bayesian methods, mainly because frequentist methods are usually taught, at least in undergrad and grad stuff. You learn on the field, so that's impressive. So I guess that to do what you do, because when people hear about a mathematician, I bet they picture in their head like someone with a pen and a paper.
Right.
But I'm not sure that's how you do stuff right now, right?
Right. I think that starting in math has given me a durable love for pen and paper work, and I still always have pen and paper with me, but most of my daily work is computing.
And so do you program a lot? How is your workflow? And maybe what's your favorite programming language?
Sure. It's evolved as I've moved from graduate school to my current job. My work has become steadily more applied and less theoretical. So programming has become more and more core to what I'm doing. My favorite programming language.
Or maybe just the one you use most frequently,
Okay. I was going to give a shout out to my recent love for Swift, which I don't use for machine learning, but I just happen to be involved in some mobile app development work and found it such a beautiful language. It's fast, it's clean, it's expressive. I hope that it becomes more popular.
Tell me more about it, because I really don't know what Swift.
It's widely used in mobile development for iOS, and it's a newer language. I think it came out in 2014.
Oh, yeah.
I used it for teaching, which has a lot of helpful features for teaching because it's strongly typed as opposed to Python. So it was a good way for students to get an idea of, okay, what kinds of objects am I passing around here? Whereas some Python can be super easy to get started, but sometimes it sweeps maybe more of that under the rug than you want if you're trying to learn. But all that said, in my day-to-day work, I use Python. I really appreciate sort of the strength of the Python machine learning community. And then I also use MATLAB some, and I appreciate the reliability and the range of some of their statistical and signal processing capabilities.
Usually when I talk to people in academia, there is still a big chunk using MATLAB. Even in economics, a lot of people using Stata. How do you decide that on this project, or at least on this part, I'm going to go with MATLAB, and there, I'm going to go with Python?
Just depends. I mean, for example, recently I was using some wavelet transformations of my data, and MATLAB just has the wavelet toolbox, which has really nice functionality for that. And it was just a little more easily accessible. Also, sometimes it depends on who I'm collaborating with. So if I'm working with somebody who sends me all their data in MATLAB, I might stick with that format.
What's the distribution of that, when you're collaborating with someone? Is it more like MATLAB, or is it more open source languages? Maybe R even? I don't know if in your community, how it's...
in my community, I haven't worked so much with R, although I have nothing against R. I've used it some. I don't know. It's a mix. And I find sometimes lately I've been translating more in terms of I'll get something as a MATLAB file and load up in Python because that's where my workflow is concentrated right now.
I have the feeling it's really specific to each field in academia, right?
Yeah, absolutely. And I think also MATLAB is what I learned on, and I've been pushing myself to use Python more and as my dominant tool just to become more versatile.
Yeah, so I guess you also learn Python on the field, right?
That's right.
Yeah.
That's right.
That's
lots of Googling.
Yeah. And actually, how do you use that in your workflow? Is it in your field? Is it valuable to put your code in open source? Or is it like really just the paper, the model, the results of the model?
It's definitely valuable to open source your software. That doesn't necessarily mean that it's prevalent, and I hope that it'll become more and more common. I know that when I'm reading somebody else's work and they don't include their implementation, it just makes it so much harder for me to compare what I'm doing or build on what they're doing or just work with it further. So it seems like there's momentum in the direction of that becoming the norm, and I hope that continues, but we're not there yet.
That's nice to see that it's moving forward, at least in your field. Sometimes it's also another work to have a rightly structured open source code versus paper,
That's a really good point, and it can be a really different skill set.
Yeah.
So maybe somebody gets code that works and implements the method that they're trying to implement for their own purposes, but if they're a newer programmer, they might just not feel comfortable sharing it with the world. And so I think that's a barrier that we also need to work to get past.
Yeah, clearly, because in science, reproducibility is
Yeah.
kind of a big objective, at least. So, yeah, definitely something to think about.
Absolutely.
That's very interesting. It reminds me of a question I often ask to the guests. It's how widespread or accepted are Bayesian methods in your field? I mean, if you want to have a caricature, it's how hard it is to find co-authors and to write papers that don't revolve around frequentist p-values.
I would say in computational neuroscience, where I did my graduate work, Bayesian methods were quite welcomed, at least in the sub-community I was in. As I said, I got into Bayesian methods because my advisor saw them as really essential tool to explore the kind of data we were working with. Now I'm closer to medicine and health, and the scene is a little bit different. I think there's plenty of interest, and that interest is growing. I think a really big factor is communication and interpretability. So you can have a stellar Bayesian model, but if somebody is eventually making a health decision based on that, they really need to understand where that advice is coming from.
Yeah.
And so I think when people are using Bayesian models in healthcare, they really need to be aware of just the breadth of their potential audience, from clinicians to patients and others far beyond their own sort of maybe machine learning community.
Yeah, totally. I guess there is kind of two different metrics or array of metrics that you report on, depending on if speaking to doctors and so on, and physicians, or if you're writing a paper, I guess. So the question would be, what's a Bayesian paper like? When you don't have p-values to report, what do you report? I guess there is several things to report, which is actually a good thing. There is not only one p-value to report, but what's it like, a Bayesian paper?
Oh, sure. Well, it's nice to be able to give both point estimates of quantities of interest and then also quantifications of uncertainty in a pretty precise way. You can do that in frequentist statistics as well, but I'm a little biased, but tend to find that the Bayesian interpretations of those uncertainties are a little easier for people to grasp.
Yeah.
For example, a frequentist confidence interval is not always super easy to grasp your head around. You might want to interpret it in terms of a simple probability, but that's not quite right.
No.
So it can be nice to report quantities of interest in terms of their probabilities in a Bayesian way. It's also, I find that reporting Bayesian results really forces you as a researcher to confront your assumptions pretty explicitly and maybe interrogate them.
Yeah.
So you have to be very open and upfront about what your priors are and how you chose them, at least if you're writing a good ethical paper or exploration of what you did.
Yeah, totally. I'm on your side for the confidence interval thing, because Bayesian compatibility interval really is what it says. I mean, it's an 80% compatibility interval really means that conditional or in your model and data, which is really important, conditional in that, well, there is an 80% chance that, I don't know, the value you're interested in is in the interval.
Exactly. It's what everyone thinks a frequentist confidence interval is.
Yeah. Right. And what's your experience with non-technical people, I mean, physicians and so on, that you work with on your project? When you report them the results of the model, how do you do that? What do you put in front of them?
That's a harder topic for me to maybe take on right now, being pretty new in my new setting at the hospital. So I think I might pass on that one if that's okay.
Yeah, of course. But that's a good thing so that you can come back on the podcast when you've got a bigger data set to report on. Definitely. I think we could dive in a little in what you do day to day right now.
Sure.
You did a lot of different things. I mean, you worked on ecological inference, right? On gerrymandering. And right now you're using Bayesian methods to better understand aspects of certain neurodegenerative diseases. I think here we are. That's the point where I'm completely clueless. So, no, it's seriously, what can you tell us about that? That sounds really interesting and exciting.
Absolutely. I'm working right now at Mass General Hospital, and we're working with data from people who have various neurodegenerative disorders. Parkinson's disease is probably the one people would know best, but we're looking at related disorders like different ataxias and ALS, for for example. And there's a lot of questions you might ask about these disorders. There are questions of classification that you might have. We have these groupings of diseases, but they're actually quite heterogeneous. And perhaps there are different subtypes within the diseases that we don't understand yet. Almost certainly there are. This is important because if you can better understand the different phenotypes of the diseases you're seeing, perhaps you could better target medication or other treatments to the people who it would help. Another big issue that needs a lot of attention is just anything that could help with early detection of these disorders. A lot of them, if you can catch them earlier, then the prognosis is better, or the treatments might be more effective. Or we might have treatments that are not effective right now because we're using them too late. So if you can detect these diseases earlier on in their trajectory, you might have better outcomes.
Oh, yeah, that's fascinating. So it means that you're building models that, based on different variables, are able to tell maybe if someone has got some disease or else, and that you can treat it earlier, right?
That would be the goal, yes. And we're getting data from a few different sources. And a goal with some of our sources are that they might be easy to use and apply outside of the clinic, because that would be helpful not only in early detection, but also even after somebody's been diagnosed with a disease. They might come into the clinic every few months, but a lot could happen in those few months, especially if you're trying out a new treatment. So we're looking at data from wearable sensors, for example, because these disorders involve movement problems, also video data and data from people performing, say, a simple task on the computer where they have to move the mouse. If these diseases are related to movement, you might expect that the way in which they move the mouse would be related to the severity or trajectory of their disease.
Oh, okay.
So those are some of our input variables.
Okay, and how do you get that, actually? I mean, is it like people coming to you and asking you if they have certain types of disease and so on, and then you put some of these wearable devices on them and so on? How is it done?
Right. So I'm not involved in reaching out to patients or research subjects directly, but my collaborators and supervisors are. And so it's great to be doing research in a hospital setting because, for example, my boss, who is a doctor, he is a neurologist. So patients come to see him for problems that they're having. And then we can invite these patients to sign up for a research study. And of course, they don't have to. There's no pressure, but some of them choose, since giving their data could maybe be helpful to other people, that they'll give it a shot and be involved. And I've been so grateful for how generous people have been in terms of getting involved in these studies.
So it means that you get to design the experiment, that you will have the data that you'll get, right? How do you decide on the variables that could be of interest to you in your models?
That's been really challenging so far, and is really at the crux, I think, of how we make all this data useful, especially because our data is pretty complex and it's temporal. There's a lot to dig into there. So if you have, say, data from 6 wearable sensors on different parts, each of which is on different parts of your body, and each of which is measuring acceleration and angular velocity and maybe some magnetometer fields over the course of a bunch of clinical tasks where you're, say, asking somebody to make a certain motion with their hand or do some other sort of standardized task. It just adds up to a pretty big volume of data. So making meaning from long and heterogeneous time series like that is a big challenge.
Yeah, because I guess you're also trying to do causal inference and not only prediction, maybe?
Yeah, maybe eventually. Yes.
Okay. Yeah, but that's not necessarily the primary goal.
Right.
Okay. So it's a little easier, I'd say, but it's already very challenging. And do you worry about the fact that maybe your sample could be biased in any way, by auto-selection in the study? I mean, like maybe people that choose to opt in have certain characteristics that are very different from people that choose to opt out?
I think that's always a challenge when you're doing a study like this. But one of the goals is that some of the work we're doing could also pave the way for future studies. Yeah. So I think that's definitely something to keep in the back of our minds. But whether it's there or not, hopefully we get directions for where we'll go next. Certainly finding healthy controls can be is maybe there's even more selection bias there, because if somebody's coming into the hospital already and you ask them to sign up for a research study, that's one thing. But if you go out recruiting, maybe there's more potential for bias.
Yeah. Definitely.
Yeah.
The interesting part, maybe the time series thing. Actually, do you use models that explicitly deal with the temporal dimension or not really?
Yes, to both. It's great to start out with some simpler models that maybe omit some of the temporal dependencies, or maybe incorporate them in simpler ways, such as by going to maybe a frequency analysis. It can just be a useful first step to see what you can pull out just from simpler features that aren't temporally dependent.
Yeah.
But ultimately, sort of deal with the full richness of the data set, we do need to model the features temporality of the data. So we are working on that too.
Okay. And are you using Bayesian methods to do that too?
I am still, again, I just started, so let me not build this up too much. But there's been really interesting work done using things like hierarchical Dirichlet process hidden Markov models. And that's a mouthful, but to extract sub-movements from movement data, and something like that could be really useful for us as well.
Okay, so that types of model can be used to model temporality in the data.
Absolutely.
Okay.
So you could think of the data as coming from some hidden Markov model, perhaps with some extra dynamics built in, and then go from there.
Yeah, so to talk about that, I think we'll have to go back to what's the Dirichlet process in the first place, because I heard that you use that quite a lot in your work. So maybe you can just start by telling us about the Dirichlet or Dirichlet. In France, we say Dirichlet, but here I noticed you say more Dirichlet, so we'll go with Dirichlet. So what's the Dirichlet part of the Dirichlet process?
First of all, I've never been sure which pronunciation is correct, but I'll stick with my habit, I guess.
As I often say, it's not the most important part of this technique.
So to start with the Dirichlet distribution, before we get to the Dirichlet process, it might make sense to take even more one step back to the beta distribution, which maybe people know and love, because we can think of a Dirichlet distribution as a multidimensional version of a beta distribution. So beta distribution, you draw a variable from it and you get a number between 0 and 1. And if you want, you can interpret that as a probability. So maybe it's the probability of heads in a biased coin or something like that. But the point is, you take a draw and you get something you can interpret as a probability. Dirichlet distribution is a generalization of that, where when you take a draw, you get a vector of numbers that add to 1. And so you can think of those as probabilities for some discrete distribution.
Yeah, like rolling a die.
Exactly.
And getting the probability of each side.
Exactly. Yeah. If you use a Dirichlet distribution with 6-dimensional vector of parameters, then you could get something that might model rolling a 6-sided biased die.
Yeah. As soon as you start working with Dirichlet, you'll have to worry about having multidimensional arrays and matrices. And
sure.
It's going to be a fun treat when your model finishes sampling. So that's the Dirichlet distribution, the Dirichlet part. And what's the Dirichlet process?
Yeah. So again, I was emphasizing that a Dirichlet distribution, when you take a draw from it, you get something that describes a probability distribution. So it's pretty meta. It's a distribution of distributions.
Yeah. Just to get a better idea, when you take a sample from your Dirichlet distribution, you get 6 probabilities. But as you have your whole distribution of the Dirichlet, you actually have a distribution of each probability.
Right.
Okay.
So you could think of, as you take more and more samples, you're getting the probability distributions for more and more 6-sided die.
Yeah, exactly.
And dice. And if you look over all of that,
then you've got the distribution for the probability of 1, probability of 2, etc. And each time it adds up to 1. The Dirichlet is there to account for the fact that everything must sum to 1.
That's right. Yeah. So each draw from a Dirichlet distribution will add to 1.
Yeah, exactly. And then, so that's when you draw from a Dirichlet distribution.
Yes.
And when you draw for a Dirichlet process.
When you draw from a Dirichlet process, you get a probability distribution over countably infinitely many elements. And And moreover, the elements themselves, the atoms of that distribution, are drawn from some base distribution. So maybe they're not just the numbers 1 through 6 for your 6-sided die, but they could be numbers that are themselves drawn from Gaussian distribution. And so you draw some numbers from a Gaussian distribution, countably infinitely many of them, and then to each of those numbers you assign a probability. And there are countably infinitely many probabilities, and they sum to 1.
Okay. So it means that when you draw from a Dirichlet process, you draw a probability distribution?
That's right.
Okay. And your base distribution, in your example being the Gaussian, it means you're drawing a Gaussian distribution?
It means that the numbers that have support under the distributions you draw from your Dirichlet process will come from the Gaussian distribution.
Okay. But it's not supposed to look like the Gaussian.
A draw typically would not.
Okay.
That's right.
It's not because one sample from the DP, so Dirichlet process, will be a distribution, but it's not because the base distribution of this DP is a Gaussian or a Poisson or any other distribution. It doesn't mean that the single draw from the DP will be a Gaussian or a Poisson.
That's exactly right. Okay. And that's a really good point because your base distribution can be continuous, as in the example of a Gaussian, as we've been discussing, but your Dirichlet process draw will still be discrete over these countably infinitely many atoms.
And actually, so that means the distribution you draw from the DP can have an arbitrarily formed shape. I mean, it could be very weird even if you draw it from a Gaussian.
That's right.
Okay. What's the goal of the base distribution then?
Yeah. So I guess to get there, maybe we can talk about some settings where you might use Dirichlet distribution itself.
Course.
So Dirichlet distributions can be useful as priors in, say, a mixture model, because you'd like your prior distribution for a mixture model to describe prior probabilities of a bunch of different possible distributions for the mixing coefficients. So you'd like a draw from your prior to look like a vector that sums to 1. So a Dirichlet process is a great choice for that.
Okay. Maybe you can quickly define what's a mixture model for the listeners.
Yeah, sure. So the way that you would generate a data point from a mixture model is you could think about it as you first choose which component of a mixture you're going to choose from, and then you draw from some probability distribution according to that component. So for example, if you have a mixture of 3 Gaussians, maybe you have with probability 1/2, 1/3, 1/6, you draw from each of those Gaussians. And so overall, to get each data point, you choose which Gaussian you're going to draw from, and then with probability 1/2, 1/3, 1/6 respectively, and then you draw from that Gaussian. And overall, the resulting distribution would look like maybe 3 different Gaussian bumps.
Yeah. And like, for instance, if we take your example, it could be like the distribution of height. It's a very classical example.
Exactly.
The distribution of heights among males, females, and maybe children.
Exactly.
So that you've got a mixture. When you look at this data set, you will have 3 bumps because it can actually be described with a mixture of 3 different Gaussians.
That's right. Okay. And in that example, your mixing probabilities would be the relative probability of somebody being male, female, or child.
Yeah.
And the Gaussian, you would have a different distribution describing the heights for each of those 3 categories.
Yeah, okay. And then to get back to the Dirichlet process, so you've got this mixture distribution that you want to model. And so the Dirichlet process comes in handy here because
often it's not super realistic that you know a priori how many clusters you have or how many components your mixture model will have. So for example, if we're trying to look for subtypes of a disease in some patient population, we might not know how many subtypes we're looking for. And maybe actually we would sort of like to just add as many components as are reasonable. So the Dirichlet process is a non-parametric alternative to the Dirichlet distribution, where you could potentially have countably infinitely many mixture components.
Yeah. And non-parametric. I find this expression very confusing because non-parametric doesn't mean at all that there isn't parameters in the model. It just means that the parameters are possibly infinite, but their number is restricted by the data when you fit the model. So it means, contrary to a parametric method where you have a fixed number of parameters, here your number of parameters is not fixed a priori.
That's right. And thanks for pointing that out, because non-parametric can actually mean you end up with way more parameters than in a parametric method.
Yeah, exactly. So you would use like a Dirichlet process in that case. I mean, you need to do some clustering, which is a term I'm sure people familiar with machine learning really know. But you don't know how many clusters there are in your data set. And then you would use this Dirichlet process to infer the number of components you've got in the data, right?
That's right.
So for instance, how is it relevant to the work you do in neurodegenerative diseases?
So really in two ways. The first is in the realm of clustering, where we might think about trying to find subtypes of a disease or that might potentially even be overlapping. And we don't exactly know what we're looking for. So to specify ahead of time the number of clusters or the number of mixture components isn't realistic. So in that realm, a Dirichlet process could be a useful prior distribution over our mixture coefficients.
And what you call the mixture coefficients are actually the probability of each data point to be in each of the cluster.
That's right.
Okay.
Another setting where it's useful is with time series data. You can think of hidden Markov models are a very useful and well-studied way to model time series data, where you assume that you have a bunch of underlying states that are not observed, and then that the observed data is generated according to some emission probability from those unobserved states. So at any given time point, you have two things. You have what you saw, and then you have some underlying state that controlled what you saw. So maybe that underlying state is somebody's disease status, or maybe it's the submotion that they're making, or maybe it's something else. But that controls the observed variable, which is maybe a sensor output, or something that you're actually measuring. This is a handy way to model a wide variety of data, but it can be tricky knowing how many states your Markov model should have. So if you don't know how many latent states are in your hidden Markov model, you could imagine that you might be looking for a flexible prior distribution that allowed for potentially infinitely many to be sort of added as needed. And again, the Dirichlet process could be useful for that.
Are hidden Markov models related to MCMC methods, or is it just another statistical terminology that's really confusing?
Well, MCMC sampling does use Markov chains, but I think if you're new to both of them, better to consider them a little bit separately.
Yeah, I'd say the same.
I mean, I guess the tie-in is that in a hidden Markov model, you consider that each state is generated only conditioned on the state before it. And that's the connection to MCMC. Yeah. So in MCMC, you sample based on the sample that you saw before. So that's why they're both Markov chains.
Okay. Yeah, it comes from that. But apart from that, it's not really related.
Right.
Okay. And you would use hidden Markov models mainly to model time series data?
Absolutely.
Yeah. Is it like really common to do that?
I would say it is pretty common, because it's a pretty broad idea to assume that there's some kind of underlying state that you can't see, and that's generating the data you're observing.
Yeah, okay, that's very interesting. Actually, in prepping for this interview, you sent me a bunch of very interesting links to papers that I put in the show notes. If I remember correctly, there are some about the Dirichlet process per se, and some other about the hidden Markov models.
That's right, because you can use a complexification of the Dirichlet process where you actually have a hierarchy of Dirichlet processes, and that can be really useful as a prior in certain hidden Markov models.
Okay, yeah, very interesting, Anna. So if listeners want to dig deeper into the topic, I guess they can start there. I'm actually getting interested more and more into time series data, so I guess I'll have a look to their hidden Markov models. This sounds really interesting. And actually, I have two follow-up questions on that before we move on, but how do you fit these models?
Oh, gosh, that's a great question.
They sound incredibly complicated, so how do you code them, and with what do you feed them?
For a model that feels fairly complex, there are some nice results that fall out, and you can create a blocked Gibbs sampler that works reasonably efficiently. So that's generally what I've been doing so far.
Okay, like a homemade sampler.
Yes. I'm just waiting until somebody who's a better Python programmer than I am codes more of this stuff up, or maybe I just haven't found the right library yet. But so far I've been making my own.
Yeah, because from my understanding, there is no package or libraries that does that out of the box.
I'm not sure. I don't want to say categorically that there isn't, because maybe
neither,
one of your listeners made one, and and if so, shoot me an email.
Okay, clearly.
But, yeah.
Okay,
Yeah.
so basically
yeah.
you're writing your own samplers.
Yeah, I guess I would also say that there tend to be some domain-specific variants, or I have wanted to make some variants of these algorithms, and so that also makes it more likely that I end up writing my own.
That's impressive, I have to say. And yeah, the other question I had is more of a challenge. I guess people, when they hear about Dirichlet process, they heard about this stick breaking process. At least I have, and it's always a little confusing. So maybe you can try and explain that, because from what I understood, it's really central to the Dirichlet process.
Absolutely. The stick breaking process is a great way to understand the Dirichlet process. You can think of a sample from the Dirichlet process as being generated in the following way. So let's imagine we have a stick, just like a stick of wood, and we're going to break it into two pieces. And what fraction along should we make that break? Well, we'll decide by drawing from a beta distribution. And the beta distribution's first parameter will be 1, and its second parameter will be something that we set. This parameter the Dirichlet process takes.
And why 1 as the first parameter? Do you know, or? Okay, because it's usually my question when I see that. I mean, why is it 1? But I guess it's
let me
not
think
that.
about that. That's a good question.
Maybe it's not that good of a question because it's never explained anywhere. So I mean, yeah, maybe it's not that interesting.
That's interesting. Yeah. So you split your stick partway along with how far along decided from this beta distribution. Then you have a stick, which is some fraction between 0 and 1. And with that stick, you put a draw from a base distribution. So your Dirichlet process takes two parameters. It takes a base distribution, and it takes this number, it's usually called alpha, that's going to be the second parameter for that beta distribution we're using to break the sticks.
You draw from the beta distribution that gives you samples from it. And with that, what do you do to the stick?
You draw from the base distribution a sample, and you break your stick. And then you say, okay, the sample I drew, it's going to have probability equal to the length of the stick that I broke in my draw from the Dirichlet process. Then I take what's left of the stick and I break it again according to this same beta 1 alpha distribution. So I break my stick. I get a number that's now probably a bunch less than 1 because I already broke off a piece of the stick, and now I get sort of some quite small fraction of the stick. And I put that together with another draw from the base distribution. And I say, okay, this draw from the base distribution, it's going to have probability equal to this second stick that I've broken off.
So the draw from the base distribution and the draw from the beta are not related.
That's right. They're drawn independently.
Yeah. You draw from the beta, you draw from the base distribution, and then you attribute to the draw from the base distribution the probability equal to the length that you just broke off from the stick. And you determine the length that you broke off from the stick with the draw from the beta?
That's right.
Okay. So which would mean, I don't know, you drew point from the beta. So it means that you broke your stick at 0.4.
Right.
And so it means that the draw you took from the base distribution is going to have a 0.4 probability.
That's right.
Okay.
And then, so if that was your first step, then now you've got 0.6 of the stick left, and you're going to break that and get something even smaller, maybe like 0.2. And you'll put that 0.2 as the probability of your second draw from the base distribution.
Okay, yeah, because you still have 0.6 to break, and then, but you have to update your beta, or...
So the beta is the fraction of the stick you have left that you break,
so you don't have
but
to
then
update
it's the actual length of the stick that gives you the probability.
You drew, for instance, 0.4 again, then you're gonna break the 0.6 length of the...
Oh, I'm sorry. Sticks. Each time you need to make a break, you'll make a new draw from the beta distribution.
Yeah, of course. But then for instance, you draw 0.2. So it means that you will break the remaining portion of the stick. In our example, it's 0.6. You will break it at 0.2.
0.2 times 0.6.
Yeah, 0.2 times 0.6, which will be the probability of your Bayes distribution.
That's right.
Oh, okay. Yeah, okay. So it's like a cumulative product.
That's right. So eventually, if you do this infinitely many times, your stick gets broken up into infinitely many pieces, but the lengths add to 1. So you've got countably infinitely many draws from your Bayes distribution, and each is paired with these probabilities. To 1.
So it gives you a distribution.
Exactly. Exactly. And the atoms of the distribution, the place where the distribution has support, are drawn from the Bayes distribution.
Yeah. Okay. And actually, do you change this Bayes distribution? Why is it of interest?
It depends on the context. So I often use Dirichlet processes in the context of hierarchical Dirichlet processes. So I might have one Bayes distribution, and so I draw atoms from that, which gives me a certain support for my probability distributions, a certain set of possible draws. And then on that, I might define another set of Dirichlet processes. So now I have a set of Dirichlet processes.
Yeah, because one is never enough.
Right, exactly. But each of them share their support.
So actually you will...
It's hard without a chalkboard.
That's why it's a challenge. So it would mean that you choose your Bayes distribution based on your
application.
You're not restricted to the Gauss. It can be a Laplace distribution or a Poisson. So
exactly.
Anything you want. A binomial, a multinomial if you want to be like really in the high dimensions.
Yeah, you've got lots of options there. And it's just going to determine draws from your Dirichlet process. Those are distributions. And what is the support of those distributions?
Yeah, really, you choose the Bayes distribution depending on your application. Honestly, I think it was quite clear. We'll see what listeners says, but
maybe edit a little of that out.
No, I think honestly, I think it's one of the first time I understood the stick breaking process. So philosophically, why you do that, Okay, and so maybe we can go talk a little about your teaching experience because you do some teaching also, if I remember correctly.
Yes, I was working at Phillips Academy in Andover, Massachusetts for a while.
Did you teach like Bayesian methods?
I did. I got to teach an elective all about Bayesian statistics, which was fantastic.
Wonderful. Yeah. So what was it like? I mean, because I guess students are not really used to these types of thinking and statistics. So maybe what were the essential skills that you were trying to instill in your students when they started learning? And on the other end, which topics did you find the most difficult to impart?
There were high school students with very strong math backgrounds. So they'd all had calculus, but almost none of them had statistics. So that was sort of fascinating because I wasn't working with or against a lot of prior statistical knowledge.
Which is better, I guess.
Yeah. So it was actually, so that was pretty great. Before we were talking about confidence intervals and how, everyone wants to talk about a frequentist confidence interval in terms of the probability of some parameter, but that's not really what you do. And so it was just great that when we were dealing with Bayesian confidence intervals, that what my students intuitively thought it would be was what it actually was.
Yeah.
So that was great.
Without their brains telling them, oh yeah, but what's it like? How do you interpret that against what I already know?
Exactly. Since they were coming from mathematical background, I think just a lot of the working through some simple conjugacy cases or things like that were really fun for them. As far as big ideas go, or what I wanted them to take away from it, because most of their first course in statistics, I really wanted them to take away this idea that you can deal rationally with uncertainty. And just because something is uncertain doesn't mean it's intractable. And it doesn't mean you can't talk about it, because you can talk about your uncertainty and quantify it.
You can even estimate it.
You can even estimate it, exactly. So that was one major goal. I wanted them to understand the assumptions that they're making when they're doing statistics, and to be able to speak about those, and to understand that progress in statistics, or when we're applying statistics, really depends on us being honest about our assumptions and interrogating them.
Yeah, that's definitely one of the things I love best in Bayesian methods. you have to specify your assumption, and you don't have to take an oath about your assumption. If people are not happy with your assumptions, you can just change your priors and see if the analysis still stands, or even if the model still samples.
Yeah, absolutely. And then I guess the third thing that I wanted them to take away was some excitement about sort of the craftsmanship of statistics and the idea that there are so many tools that are out there, and the more experience you get, the more tools you have, and the more you can choose the right one for the job. And that's really important and exciting.
Yeah.
Also that domain knowledge is something to be respected. And if you don't have it, that can be just fine. But as much as you can acquire it and especially collaborate with people who do, you're going to be doing better statistics.
Yeah, exactly. And were there any topics they particularly found hard to understand?
I would say something that was a little bit of a challenge was that many of them did not have a computing or programming background.
Okay.
And so there were a lot of things that I thought, man, this would be a lot more intuitive if we could all just code it up together. But that wasn't that helpful for them. Or we did a little bit of coding, but that was sort of, a learning barrier in itself, not the thing that kind of led to an aha moment.
I guess that's some of the difficulty of this teaching, because from what I understand, you have to deal with all the theoretical and even philosophical stuff about Bayesian statistics. That's one thing, and it can be really hard, because I remember it took me quite a while to understand really what was the difference between prior predictive distribution, posterior predictive distribution, for one thing. And it's absolutely important to understand that. And at the same time, well, you have to understand how to code and how to program. So you have to learn that too. And then you also have to learn about the computer and how to tell to the computer how to sample, because usually your model, when it's hard enough, won't sample at the first time. So I guess these kind of things can be overwhelming. Yeah. I guess it's easier when you get a class like your student had. So I think we'll get some emails thanking you about this elective class.
I hope they had fun. I hope it inspires them to do more.
Yeah, I hope so too. Well, thank you very much, Karin. We're almost up, but before letting you go, I'm going to ask you the two questions I ask every guest on the show. So the first one is very simple. If you had unlimited time and resources, which problem would you try to solve?
Very simple. Wow, that is a delightful question. I'm not sure what my answer is. I'm really happy to be where I am right now. I think working on the intersection of sort of statistics and machine learning and health is a really exciting place to be right now. I think there's so much potential for all these awesome statistical and machine learning ideas that are being developed and improved on all the time to actually help people be healthier and live better lives and enjoy their lives more. And so I'm super excited to be part of that.
Yeah, you bet.
In a small way.
Yeah. I had bet with myself that would be your answer. So, but okay. And second question is, if you could have dinner with any great scientific mind, dead, fictional, or alive, who would it be?
Well, this is out of the statistics box, but I went to a talk by Jane Goodall a couple of years ago, and I just think that she's a superhero. She has a razor sharp scientific mind and really deep empathy, and uses her stature to make the world a better place. So I would love to have dinner with her and pick her brain and chat.
Yeah, I understand you. So I hope she's listening. Well, Karin, thank you very much. It's been a great pleasure having you on the show, and I really enjoyed this dive into your work. And yeah, as you said, your work is both fascinating, essential, and completely unfamiliar to me. So I hope this will inspire our younger listeners into doing work that really counts, as you said. And I hope that we also motivated our audience to learn about and try Dirichlet processes in their own modeling workflow. I think we understood that it could be a very powerful technique and quite versatile from what I got. And I encourage everyone, of course, to take a look at the resources I put in the show notes. So thank you again, Karin, for taking the time and being on this show.
Thank you so much. It's been a pleasure to be here.
Thanks. This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and subscribe to the show on your favorite podcatcher, and visit learnbayesstats.envol.app for more resources based on today's topics, as well as access to more episodes that will help you reach true Bayesian state of mind. That's learnbayesstats.envol.app. Our theme music is Good Bayesian by Baba Brinkman, feat. MC Lars and Mega Ran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. Thanks so much for listening. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.